Hey everyone, and welcome back. Today we're going to be tackling something pretty amazing.
Yeah,
It's something that really revolutionized physics,
it really did. And
and as the photoelectric effect.
Einstein's explanation of it, yeah,
Yeah.
absolutely.
So today we're going to be diving deep into the
Yeah.
source material
Okay.
and trying to figure out just how revolutionary this discovery really was.
So the photoelectric effect itself is pretty interesting.
Okay.
What we have is a phenomenon that was discovered way back in the late 1800s.
Wow. So this is even before Einstein.
Oh, yeah, way before Einstein. Nobody could explain what was going on.
Really?
Yeah, it was like a puzzle with like
Yeah.
a bunch of missing pieces.
So what was the puzzle exactly?
Well, you have scientists.
Okay.
They're shining light on metal.
Oh, okay.
And sometimes electrons are flying off and sometimes they're not.
Mm.
And it was really confusing them.
So they're just like shining different light on metal.
Yeah, they're like,
And sometimes electrons come out, sometimes they don't.
Exactly.
And they don't know why.
And they don't know why.
Okay.
So the expectation was that the brighter the light,
Okay.
the more energy the electrons would have when they were ejected.
Uh-huh.
But that's not what the experiment showed.
Really?
Yeah, it turned out that it was the color of the light
The color.
or the wavelength that determined the energy of those ejected electrons.
The brighter light, meaning
Yeah.
like more intense light didn't matter as much as just the color of the light.
It's really strange, isn't it?
Yeah, that's very strange. Like
That's not what I would expect.
yeah, it's not what you'd expect if
Yeah.
you're thinking about light as a wave.
Right.
So think about this. Like
Okay.
if you're trying to break a thin sheet of ice,
All right.
you could throw 100 tiny pebbles at it.
Yeah.
And they might make some cracks,
Okay.
but it wouldn't shatter the ice.
Right.
But if you take one heavy rock, even if you throw it gently,
Yeah.
that could crack it right open. Okay, so it's about the energy like in each like individual hit,
Exactly.
not the total number of hits.
That's the key insight. It's about
Okay.
the energy per hit.
So, but light is a wave, right?
Right.
So how can we even talk about it like it's individual hits?
So that's where Einstein comes in.
Okay.
In 1905,
Okay.
this 26-year-old,
Right.
working at a patent office, no less,
Okay.
proposed this really radical idea.
Okay.
What if light wasn't just a wave,
Yeah.
but also existed in these discrete packets of energy?
So he's saying that light is both a wave and a particle.
Yeah, that's exactly what he's saying. It's
Like
this
that.
crazy idea.
How is that even possible?
It's mind-blowing, isn't it?
Yeah.
But his idea really explained the puzzle of the photoelectric effect.
Really?
Yeah, what he said was each of these packets of light, which he called photons,
Photons, okay.
carries a specific amount of energy.
All right.
And that energy depends on the frequency of the light or the color.
Okay.
So a blue photon has more energy than a red photon. Oh, okay.
Yeah.
I'm starting to see how the pieces fit together now.
Right.
So if a photon has enough energy when it hits the metal,
Yeah.
it can knock an electron loose.
Uh-huh.
And the color of the light determines how much energy each photon has.
Exactly.
That's why blue light, even if it's dim, could eject electrons.
Right.
While red light, even if it's super bright, might not.
It all comes down to the energy of the individual photons.
Okay, so it's like those pebbles and that rock.
Exact.
The blue photons are like those individual rocks with enough energy to break the ice,
Each one packs a punch.
even if there aren't many of them.
Exactly.
Okay, this photon idea is crazy.
It is wild.
But was there any way to prove that Einstein was right?
Well,
Did anyone actually, see these photons?
you can't actually see a photon,
Okay,
but you can see the effects.
All right.
So there was this physicist named Robert Millikan,
okay,
and he was initially pretty skeptical of Einstein's theory.
okay.
He actually set out to disprove it.
But through a really careful series of experiments, he ended up confirming it.
So he's trying to disprove it, and he ended up proving it.
Yeah, it's kind of a funny story.
That's a great story.
Yeah, science is full of them.
So what did his experiments show?
Well, he measured the energy of the ejected electrons with incredible precision,
Okay.
and he found that it matched up perfectly with Einstein's predictions
Wow.
based on the energy of the photons hitting the metal.
Okay.
And in fact, he even calculated a very precise value for this really important constant in physics
okay.
called Planck's constant,
Planck's constant.
which relates the energy of a photon to its frequency.
So Planck's constant, it's kind of like a bridge between the energy of these tiny photons
Yeah.
and the light we see every day.
It connects those two worlds.
Okay.
Yeah, it's this tiny, tiny number
Okay.
that governs the quantum world,
The quantum world.
the world of atoms and photons.
Okay.
And what it tells us is
Yeah.
that energy in the quantum world isn't continuous, but it comes in these discrete packets
Okay.
defined by this constant.
So even though we see light as this continuous flow,
Right.
it's actually like a stream of these tiny energy packets,
Exactly.
each with its own little, like, defined amount of energy.
Like little bundles of energy.
Yeah.
Yeah. It's kind of like finding out that water isn't actually this smooth flowing substance,
Right.
but is made up of tiny individual droplets.
Yeah. Okay.
Yeah.
That makes sense.
So this idea that light behaves as both a wave and a particle is known as wave-particle duality.
Wave-particle duality.
And it really revolutionized physics.
Wow.
It led to a whole new understanding of how light and matter interact and how they behave at the most fundamental level.
Wow. Okay.
Yeah, it's pretty amazing stuff.
So,
Yeah, and you know what's really cool about this wave-particle duality?
what's that?
It's not just some abstract concept.
Yeah.
It has real-world implications.
Okay, I'm all ears.
Ugh.
How does this duality show up in our everyday lives?
Well, think about digital cameras for a second.
Okay.
They capture images using sensors,
Uh-huh.
and those sensors rely on the photoelectric effect.
Oh, okay.
When light hits the sensor,
Okay.
photons knock electrons loose,
Right.
and that creates an electrical signal that's used to create the image.
Yeah. So every time I snap a photo,
Yeah,
I'm actually capturing the energy of those individual photons
you got it.
hitting the sensor. That's kind of poetic.
It is, isn't it?
Yeah.
And it's not just cameras either.
Oh, really?
Solar panels work based on the same principle.
What?
Yeah, photons from sunlight knock electrons loose in the solar panel material.
Okay.
And that flow of electrons is what generates electricity.
So this seemingly obscure effect
I know, right?
is actually powering our homes
Just amazing.
and letting us capture memories.
It's pretty impressive for something discovered over a century ago.
It really is.
Yeah.
So you mentioned that this was actually one of 3 groundbreaking papers
It was a busy year for him.
that Einstein published that year.
It really was.
What were the other 2 about?
Well, the other 2 were on Brownian motion and special relativity.
Oh, wow. Okay, so
Yeah.
Brownian motion.
Brownian motion is the seemingly random movement
Okay.
of particles suspended in a fluid.
Okay.
And Einstein provided a theoretical explanation for it,
Wow.
which actually helped to confirm the existence of atoms and molecules.
Oh, wow.
And then his theory of special relativity,
Yeah.
that completely changed our understanding of space-time and gravity.
1905 was a busy year for Einstein.
It was a good year.
Yeah, it seems like it. Okay, so let's get back to the photoelectric effect.
Okay,
You explained how photons knock electrons loose,
right.
but is there more to it?
Well, there is one more piece to the puzzle.
Okay.
It involves photons having momentum.
Momentum. Okay.
Yeah, so you see
Yeah.
Einstein's famous equation, E-F-E,
Oh, yeah.
establishes this really important relationship between energy and mass.
I think I vaguely remember that from high school physics.
Yeah, it's a famous one.
But how does that relate to photons and momentum?
Well, since photons have energy,
Okay.
according to Eve's C,
Uh,
they must also possess an equivalent mass.
so they have mass.
It's a tiny, tiny amount,
Okay.
but it's there.
Okay.
And if they have mass,
Yeah.
even though they're traveling at the speed of light,
Right.
they can have momentum.
Hold on. How can something without mass have momentum?
That's a great question.
Isn't momentum like all about mass in motion?
That's how we think about it in our everyday world.
Right.
But the quantum world, it kind of throws our intuition out the window.
Okay.
In classical physics, you're absolutely right.
Yeah.
Momentum is mass times velocity.
Right.
But for photons, momentum is actually determined by their wavelength.
So even though they're massless,
Yeah,
they still pack a punch.
they do.
Okay.
Okay.
So are there any real-world examples of this photon momentum?
Absolutely. One really cool example is radiation pressure.
Okay.
It's the force exerted by light on objects.
So the force of sunlight.
Because that's pushing on objects.
Yeah, it's a tiny force.
Okay.
But in the vastness of space, it can have pretty significant effects.
Like a solar sail.
Exactly. You got it.
Okay.
So the concept of solar sails has been around for decades.
Okay.
And in recent years,
Yeah.
there have been some really successful demonstrations of this technology.
Oh, wow.
LightSail 2, a spacecraft launched by the Planetary Society,
Okay.
actually used a solar sail
Wow.
to navigate in Earth's orbit.
So something as seemingly ethereal as light
I know, it's amazing.
can actually exert a force
Yeah.
strong enough to propel a spacecraft.
It's mind-blowing.
That really highlights the consequences of Einstein's insights
It really does.
into the nature of light.
It shows that even these theoretical ideas
Yeah.
can have really practical implications.
It's a testament to the interconnectedness of different scientific fields.
It really is.
Who would have thought that a discovery about the photoelectric effect
Right.
would one day lead to a new form of space travel?
Yeah.
That's the beauty of science. You never know where it's going to lead.
Yeah, it really is amazing to think about how a phenomenon like over a century old is still driving innovation today.
Absolutely.
I wonder what Einstein would think
Oh, I think he'd be thrilled.
about things like solar sails and all these other technologies.
He was such a curious guy, always emphasized really understanding
Right.
the fundamental principles of the universe.
Yeah.
I think that he'd be so delighted to see that his work
Yeah.
had led to such practical applications.
Okay, so getting back to this idea of photons
Yeah.
having momentum,
Mm-hmm.
it's still kind of hard to wrap my head around.
I know, it is a tricky concept.
Yeah. If they're massless, how can they push on something?
Yeah, it's definitely counterintuitive. The
Yeah.
key is to remember that momentum
Yeah.
in the quantum world
Yeah.
is a bit different from
Yeah.
how we understand it in
Yeah.
our everyday experience.
Okay.
For photons, momentum is related to their wavelength,
Okay.
not their mass.
So think of it this way.
Yeah.
Imagine two waves crashing on the beach.
Okay.
A wave with a shorter wavelength,
Mm-hmm.
meaning the crests are closer together,
Right.
carries more energy and will hit the shore with more force.
It's a good analogy. It's
Okay.
a similar thing with photons.
So a blue photon with its shorter wavelength
Exactly.
would have more momentum than a red photon,
That's right.
even though both are massless.
Yeah.
It's like the difference between being hit by a gentle ripple
Uh-huh.
versus a powerful wave.
You got it.
Okay.
And that momentum, though it's tiny,
Yeah.
can really add up to have real-world effects,
Yeah.
like propelling a solar sail through space.
Right. It's a reminder that
It
even
is.
that's seemingly insignificant
Absolutely.
can have a really profound impact
Yeah,
when we look at things from a different perspective.
for sure.
So for our listener
Yeah.
who's been with us on this deep dive into the photoelectric effect,
It's been a great journey.
what's one key takeaway
Oh, that's a good question.
you'd like them to walk away with?
I'd say the most important takeaway is just that the world is full of wonder and mystery.
For sure.
There's so much we still don't know about the universe.
Yeah.
But that's what makes science so exciting.
Yeah.
Like
Incredible.
questioning and exploring and challenging our assumptions,
Right.
we can continue to uncover really amazing truths
Yeah.
about the world around us.
It's a reminder to never stop learning
Absolutely.
and to always be open to new ideas.
Yeah,
No matter how strange or how counterintuitive they may seem.
and I think that's a great point.
Who knows what other groundbreaking discoveries are
Yeah,
waiting
yeah.
to be made?
And sometimes the most revolutionary ideas
Yeah.
come from the most unexpected places.
Right.
Like a young patent clerk
Yeah.
named Albert Einstein
Yeah.
who dared to look at light
Right.
in a whole new way.
So to our listeners,
Yes.
keep that spark of curiosity burning. The next time you snap a photo,
Mm-hmm.
power up your laptop,
Right.
or even gaze up at the stars,
Yeah.
just remember the incredible story
Yeah.
of the photoelectric effect
For sure.
and the power of human curiosity
Yes.
to unlock the secrets of the universe.
Absolutely.
Until next time.
See you then.